Okay, so what are we going to do about Z? Well, it's intuitively getting a little difficult to visualize, but clearly if we hold R constant, Z is not going to be some constant number, okay? Because the ellipse is elongated in the Y direction as opposed to the X direction, going around at a fixed distance from the Z axis. It is not going to give us anything set. Okay, so what do we get? Well, first of all, we just solved this for Z, right? So Z is going to be plus or minus 3 times the square root of 1 minus x squared minus y squared over 4, right? Well, that's easy enough. We know what x and y are, so now it's easy enough. The question is, what are we going to do when we see this as a limit on the integral? I don't think it's going to be pretty, okay? And I won't even ask you to do this one in spherical coordinates because I know it's going to be terribly ugly, okay? Because you don't have any spherical symmetry and you don't have cylindrical symmetry. No kind of symmetry on the cylindrical. Because of what I just said, if you hold R constant and take theta all the way around, you go up and down, right, as you go around.
Didn't someone design spherical and cylindrical to do things like this?
No. I'm trying to convince you that often there's one coordinate system that's much easier than the others. Okay? Now for a sphere, the spherical is the easiest, the cylindrical is next easiest, and the rectangular is next easiest, but none of them are that bad. The worst thing you get is rectangular, where you got to do a little more trig substitution. Okay? But they're all straightforward. At least you're trying to find volume if you don't have a complicated density function or something. And if you do moments of inertia, as long as your density function is reasonably well behaved with some kind of symmetry, it's not bad in any coordinate system. But probably easiest if you're doing things about an axis, if it's the z-axis and you use cylindrical. Okay? Depending on the kinds of symmetry you have, and you just have to get used to that and identify it. Okay? Okay, so anyhow, you're going to have what? This plus or minus 3 plus or minus 1 minus r squared cosine squared theta minus r squared sine squared theta over 3, right? Now, we don't have time because we've got about 4 minutes left. Okay? So we go through all the partitioning, and I want you to think through how that would look. Same idea. Just different symbols that you're partitioning, but, you know, what's it look like? Remember that your volume increment is r, dr, d theta, dz, right? And if you get the volume of your typical partition, you see that, and we've done that with the spherical. And it's no different. It's just that these things are a little uglier, way uglier. So we get the integral then. First of all, from 0 to 2 pi, with respect to theta, and I'll just do the volume integral, but because I don't want to have to write in too much stuff because I don't have enough room or time. Then we're going to go with respect to r, because r depends only on theta. Okay? And you know what?
I really just want to show you the thing. I thought it was going to be the only time until Friday. He told us that we could take it on Friday. I was like,
Now your limits on r actually depend on both theta and z, so this is totally wrong. We have to partition the ellipse in the z-plane before we can do this. Reason being that above this ellipse you have points that are all the way out here, and there are no points above. You know, above you have, okay? And I didn't realize that till I wrote this down, and I wasn't thinking clearly. This is what I'm used to doing in cylindrical coordinates. So again, it's totally screwed up. But you would start by trying to take r from negative square root of
Log 2 equals 2 x thing.
4 over 4 cosine theta
You're supposed to solve them.
plus sine squared theta
Yeah, I just like did this.
to the positive square root of the same
It's not
thing.
like that.
Okay? Of course, you could make it 2 times 1 over this, factor out that 4.
It was like a big balance down to the.
But since I tend to forget the 2's here, I've decided to leave it inside. Okay, then you're going to have z, but z really doesn't do this for all values of r. Because depending on your r and theta, you could get a negative under the square root. Okay? If r is big enough, and theta, cosine theta and sine theta are just right, because you could get something that doesn't even work. Okay? So okay. So I'll just say we have to end up using 0 less or equal to theta less or equal to 2 pi. And then our ellipse is instead of x squared plus y squared over 4 equals 1, it's one minus z squared over 9. Okay? For fixed z. Okay? And then you have to adapt that. Well, it's just going to be this, but you're going to also have a square root of 1 minus z squared over 9 as a factor on your r. Okay? So z is going to get to go from okay? And then r is going to end up going from I don't have room to write that one, I'll write the one over here. And I'm not even going to double check this, but I'm pretty sure it's right.
Thank you.
This and then negative x square root. So kind of think that through. It stretches your ability to work with the different coordinate systems. Okay? Then think of what you'd have to do if you tried to describe this thing in cylindrical coordinates.
Spherical?
Yeah, we just did it in cylindrical. Obviously spherical. What'd you think cylindrical for? Okay, got it?